So today in class we discussed how to use a combustion analysis to determine the empirical formula of a hydrocarbon. Let's extend this by taking a look at number 69 in this problem set. And in this problem we're given data where we're told that we have 135 milligrams of a hydrocarbon. We could also write this as 0.135 grams. And I think it'll be easier for us to convert grams to moles than milligrams per millimoles, although we would use the same conversion factors. So that I can give you this two different ways. Let's go from milligrams to millimoles. So this hydrocarbon, which of course is only going to have carbon and hydrogen atoms, is subjected to combustion, which means I react it with O2 gas, and it's going to produce CO2 gas plus liquid water. And we are given the amounts of the products. We have 440 milligrams of CO2 and 135 milligrams of H2O. Now we're also given a piece of information that we have not yet used, and I want to briefly discuss it on this video and then also use class time tomorrow to discuss it, and that is the molar mass of the hydrocarbon. So we've been calculating empirical formulas, but the next step for us is to be able to calculate the molecular formula. And in order for us to do that, we do need to know what the molar mass is. So let's start off in much the same way we did in class today, finding out what our mass of carbon is and what our mass of hydrogen is. So we have 440 milligrams of CO2, and from a molar mass analysis I know that 12.011 milligrams of carbon are in 44.01 milligrams of CO2. And of course milligrams of CO2 are going to cancel, and I'll be left with an answer in terms of milligrams of carbon. So all I need to do at this point is to use my calculator to simplify this expression. So we have 440 times 12.011 divided by 44.01, and I obtain an answer of 120.082708 milligrams of carbon. I can repeat a similar process for hydrogen. I know that this reaction will produce 135 milligrams of water, and I know that for every 18.02 milligrams of water, I have 2.02 milligrams of hydrogen. Again, milligrams of water will cancel. And when I simplify my expression, I will obtain how many milligrams of hydrogen I need. Now, you may be wondering if this calculation is necessary, and you would be right in saying no. Since I know there's 135 milligrams of total mass, and since I know the mass of one of the two components, then the other component has to be the total mass minus the mass of carbon. So we're looking for an answer that's around 14.9173 milligrams. But in the beginning of doing these problems, it's a nice check for us to have. So we have 135 times 2.02 divided by 18.02. And the answer that I get is very close to what I mentioned, 14.92. I did do a little bit of rounding, so that should not surprise us. My advice is to do as little rounding as possible, because the more rounding you do, the more error you're going to introduce into the problem. So as we prepare for this next step, we know that we have 120.082708 milligrams of carbon. I'm going to convert this to millimoles. I know that in 12.011 milligrams of carbon, there is 1 millimole of carbon. Now, we haven't talked about millimoles in class, but a mole of substance is equal to the gram formula weight. In grams, a millimole of substance is equal to the milligram formula weight in milligrams. So we often start with simplifying assumptions, and then as we get more seasoned in our problem solving, we want to be able to, unzip another layer of truth, and that's really what you're being exposed to right now. So I'm going to convert this to millimoles. I have 120.082708 divided by 12.011. That is 9.97727 millimoles of carbon. Now I went back and recalculated the mass of hydrogen using a more precise molecular weight, and I got 15.1062597 milligrams of hydrogen, and I know 1.0079 milligrams of hydrogen is 1 millimole of hydrogen. Same logic that we used for carbon. So 15.1062597 divided by 1.0079 is 14.98785556 millimoles. Now we're to the point where we were with our easier, more straightforward empirical formula problems. Now we simply want to divide by the lowest number of moles. That's going to be 9.9977277, and I get 1.4991261, which I clearly want to round to 1.5. And of course, any number divided by itself is 1. I need a whole number ratio, so I'm going to multiply both the 1 and the 1.5 by 2. That gives me 2 atoms of carbon, and that gives me 3 atoms of hydrogen. This is the empirical formula. Similar to what we did in class today, this one's a little bit easier. Remember, we ended up with a fraction of 1/7, so we had to multiply everything through by 7. Here we have a half integer and a whole integer. We multiply both of them by 2. Now, if we go back to the original problem, we were given the molecular mass, the molar mass, of 270 grams per mole. I also want to know what the mass of the empirical formula is. By the way, this is 27. 2 times 12 is 24, and 3 times 1 is 3. I'm rounding these to whole numbers. I think you'd have to agree that 12.011 rounded to 12 is reasonable. 1.0079 rounded to 1 is reasonable. 27x is equal to 270. Solving for x, of course I'm dividing both sides by 27, I find that x is 10. I'm going to multiply the empirical formula by 10 to obtain the molecular formula. This will be C20H30. This is the molecular formula. Sometimes the molecular formula and the empirical formula can be the same. Other times the molecular formula will be some integer multiple of the empirical formula. I'd like to take a little bit of time in class tomorrow to go through one of these. I will not be taking as much time as I did in class yesterday, but I think we can budget about 15 minutes to do one of these before it's time to move on to the next big thing for us.